Hello everyone, my name is Agnes Blom-Schieber and I'm a Technical Fellow with the Boeing Company. Today I will be talking about an example in optimization applied to an engineering problem as an illustration of some of the lecture material that you've seen in the past. This particular example will be on advanced fiber reinforced composites, and I will discuss concepts such as how to define your optimization problem, both the variables as well as objectives, where constraints might come from, and how you might want to deal with them. While I discuss setting up your problem, I will also mention where I've applied symmetries, made use of chains of variables, and things like surrogate models, or how design spaces might influence the outcome of your optimization. And finally, I will spend some time on how to validate your optimization results. As with any engineering analysis, optimization could give you, nonsense answers, and there will be a couple of things that are good practices to make sure that whatever you produce actually makes sense. Now, all of this will be done using a somewhat real-life example, although it's still fairly academic. It does have a lot of the elements that we do encounter in bigger real-life applications. And in order to make sure that you can follow along, I will give you some background information on what a fiber reinforced composite is and the manufacturing methodology of automated fiber placement, because that will play an important role in defining both the variables and the constraints. When I talk about the composites, I really mean a fiber reinforced composite, where the fibers, if you have a layer of material, and if my fingers are the fibers, they really provide a lot of strength and stiffness in the direction of the fiber. So if I pull on a fiber, it's very strong and stiff. But if you pull perpendicular to the fiber, then you don't have as much stiffness or strength. So the fiber is held together with a matrix material, and together they give you behavior that's different than, for example, an aluminum or a metallic structure, because now you will have different properties in different directions. In the aerospace industry, we're taking advantage of that by using more and more composites to reduce the weight of our airplanes and thereby reduce fuel consumption and have a better airplane in terms of both economics as well as for the environment. So here you see an illustration of what a composite laminate is. It's multiple layers of materials that can each go in different directions. And if you want to tailor your laminate to a specific load condition, you can change, you can have more fibers in one direction than in another, as you can see on the far side there, where we have two layers in the 0 degree direction, and thus you would have higher stiffness and strength in that direction. But you can also play with the number of layers, so you can make it thicker, and then play with all kinds of combinations to really tailor your structure to the loading situation that you have. In addition, you have a lower density than aluminum, so a higher strength to density ratio, and it's easier to integrate parts, so you don't need as many fasteners. Well, I will really focus on kind of the first two items here, and then we go one step beyond that. So normally, as you saw in the pictures that I showed, every layer has one constant fiber orientation. So you can see here, these lines are straight, so they kind of represent a constant fiber angle within a layer. However, with the advanced manufacturing technologies that we have, such as automated fiber placement, you can even kind of steer the fibers and have them vary the orientation within a single layer. So orientation drives your strength and stiffness. So now you can make the strength and stiffness vary within one layer without having to change the number of layers. You see an example there on the far side where this was just a manufacturing trial. You can see a lot of arcs, but you can go, S shapes, all kinds of shapes, as long as it's a continuous fiber path. And here you see a video of one such system where it's laying these strips of material down. In this case, the black is the carbon. And you can kind of see the bands of material go around the curve. And if you design your structure to intentionally have varying fiber angles, this machine or the more industrialized versions of this machine can be used to manufacture it. However, there are limitations to this manufacturing technology. Depending on the width of the material that it's laying down, you may or may not be able to steer more tightly. So there is a radius of curvature. That's a limitation. If you go too tight, you might encounter these small puckers, like little buckles on the inside of the radius, and that's something that's not desirable in terms of quality. So therefore, when you design, you want to make sure that this steering radius is above the minimum threshold for your material and your tape width. So that's really the introduction of composite materials and the limitation that we have on the manufacturability of these advanced laminates. The engineering problem that I was studying in this example was a cylinder in bending. You can imagine a fuselage with passengers undergoes bending when you have when you're in flight or when you're taking off. And as always in aerospace, everything that has to come off the ground takes fuel. So the lighter we can make our structure, the better it is. So the optimization goal is to minimize weight. Now, in this case, the assumption was that we have the same number of layers everywhere. So the only way to reduce weight is to change the number of layers or reduce the number of layers. But if each layer can be steered, then we have an additional set of variables for each of the layers to define what this machine has to do and what kind of fiber angles you get out. Now, here comes the first problem. If I change the number of layers, I will also change the number of variables that I need during my optimization. This is called mixed integer optimization. There are algorithms and methods out there that will allow you to change the number of variables and use continuous variables in the same problem. But in this case, I actually just chose to do multiple optimizations with different numbers of layers. So for example, the baseline cylinder had 24 plies. Then I looked at one where I had 23 plies, ran the optimization for that, ran the optimization for 22 plies, etc., until I could no longer find a feasible solution. It's extra work to set up all these problems, but it is one practical way of solving it. So what I will talk about in the next couple of slides is one of these problems where I just picked kind of the baseline number of plies and said, okay, well, can I show that I can improve the performance at the same weight? So this was kind of the reformulated problem. The objective now is to maximize the load carrying capability of this cylinder in pure bending. And the variables that were left are the parameters that define the steered layers. I already kind of jump ahead here with a picture that says 5 variables per ply. I will come back to that. I also want to point out that I will use the words ply and layer interchangeably. They mean the same thing. As for constraints, there are structural constraints, things like deflection or buckling load, overall laminate strength, those kind of things, as well as manufacturing constraints. The radius was one of them. There were a couple other constraints to which I'm not going to go into detail, but those are typically, if you're a mechanical engineer or maybe a civil engineer, those are typically the kinds of things that you run into when you do an optimization. And one that was not applicable to this problem, but can be applicable to a lot of design problems, would be spatial constraints, making sure that things don't run into each other or poke out of something. And that's something that you encounter regularly. So in the next couple of slides, I will talk about how I came up with the design variables. How did I use my engineering knowledge to define these variables and kind of make sure that I had an optimization problem that actually was doable, I'm going to say. So the first question I asked myself, how do I define a steered ply? When I define one, the things that are important are the fiber angles. As a structural engineer, that's what really drives your structural behavior. But then the path that the machine has to follow is another one. And those two are directly linked with equations. So you can't decide on those independently. And then, how many control points? It kind of goes with the first question, and I'll walk through my thoughts on that. And then, how many and which plies to steer? If you have 24 total plies or layers, how many of those are going to have a unique definition? So the first place to start is you ask yourself, what are my requirements? If we look at our requirements from structural consideration, then we say, okay, we have this cylinder and it's in pure bending. And in this case, that means that the top here is in tension and the bottom is in compression. And assuming that the ends are kind of fixed to a plate, your displacements as a function of your vertical coordinate is going to be linear. So around the circumference of your cylinder, you will have varying loads going from tension with periodic equation to compression at the bottom and back. You might have some boundary condition effects if you look at the axial direction, but by and large, there's no significant loading variation along the length. We don't have any shear, so the bending moment is constant, and so you'll have a constant loading along the length. And then when you look at this cylinder and you kind of draw this, vertical plane, the left and the right-hand sides, should behave symmetrically because my load is symmetric. So again, you have the cylinder cross-section there. The vertical line would be kind of your vertical plane. Now, so that's from a loading perspective. Now, from a manufacturing perspective, we have these fiber paths, and here you can kind of see an illustration of two layers kind of superposed on top of each other. But when you have a cylinder, you can think of it as a flat sheet of paper like this, and you have these paths, but it wraps around. And so when you come around this cylinder and you come to the top, your fiber paths have to continue because your machine has to keep going. If your fiber paths don't link up at the top, your loading won't be nice and continuous, and you're kind of going to have a seam there. So your fiber angle definition and your path definition have to make sure that your paths can wrap around there. Now, those two things together basically drove my first decision. Since I don't have any real loading variation in the axial direction and mostly variation in the circumferential direction, I said, I'm going to stick with a one-dimensional angle variation, and it's going to vary as function of the circumferential coordinates. Now the second decision is, okay, so now I have a function that I have to define. And how am I going to define it? I've already narrowed it down a little bit because a two-dimensional variation is gives you a lot more choices than a one-dimensional variation. So I started looking around, and based on some other literature, I thought, okay, I can have a piecewise linear angle distribution, and I will have a plot in the next slide. Or I can have a piecewise constant curvature distribution, which basically means I have circular arcs, and at the point where they connect, the fiber angle is going to be continuous, but the curvature will change. And then the last one is using splines. Could be a Bezier curve, it could be B-spline. There's different choices there. It's more of a thing that mathematicians are more familiar with rather than most engineers. But again, I will try to illustrate that here. So there are two plots here. The top plot has the circumferential coordinate at the bottom, and just for illustration purposes, it only goes to 180 degrees, but of course in reality it goes to 360, and you go all the way around the cylinder. On the vertical axis, you will see the fiber angle, and this fiber angle can go from, in theory, from 0 degrees to 90 degrees, where 0 degrees goes along the length of the cylinder and 90 goes in the circle, in a hoop, around the circumference. And here you see two of the three options that I mentioned, the piecewise linear and the piecewise constant curvature. And in this case, I defined the fiber angle at every 45-degree increments. So you can see here, at 0 degree, I set it to 10. At 45 degrees, I set it to 10. So that's a constant angle, right? Nothing special about it. But at 90 degrees around the circumference, the fiber angle goes up to, I believe that was 25 degrees. And the one thing that you might notice is that the piecewise linear and the piecewise constant curvature angle distributions are very similar. Now you can continue that, and what you see at the very last leg of these piecewise distributions is that when the difference between the two fiber angles for each segment is pretty big, there's going to be more deviation in the fiber paths. But assuming that that's not drastically different, I said, okay, well, I guess it doesn't really matter which of these two I pick. Now, the one reason why I might want to pick the piecewise constant curvature, remember the circular arcs that are connected, is that the curvature of this path is constant for each section. So for the piecewise linear one, it actually varies as function of this circumferential coordinate at every single location. And so if I want to look at this curvature, or the radius of curvature, I would have to compute it at every spot between 0 and 180 degrees. Whereas for the piecewise constant curvature one, I only have to evaluate it once for each segment. So here I've shown 4 segments, which would mean I would have 4 values for curvature that I have to check for and make sure that they're within the bounds. Now that's the engineering view of things, the fiber angles. Now here at the bottom, you can kind of see the actual distance as and the kind of the path that it takes. And I will see if I can kind of recreate that. So on the horizontal axis, we had our actual distance, which I'm going to call x, and this is y, which is basically your cylinder radius times your circumferential coordinate. And it kind of looked like something like this, right? This was a fallout of the angle distribution that we had put together. Now, if you use a spline to define your fiber paths and your fiber angles, instead of first defining the fiber orientations, you would first define the path. So this might look like this. And so this is the path, right? And then from there, you would go and you would derive the angle as a function of this circumferential coordinate. And let's say, it might have been 10 and then something happens. So kind of the order of computations is the other way around. Your variables describe this and your angle falls out. Whereas with the piecewise distributions, you define the angle and your path falls out. Now, in terms of the actual optimization, you can give either one to the computer and the computer will figure it out. As an engineer, if I had to define my structure, I like to think in terms of fiber angles. And so in addition to the comments about the curvature being very easy to calculate for the piecewise constant curvature definition, it also is more intuitive from an engineering perspective. And so that's why my second decision for defining my variables was to use this piecewise constant curvature function. Now, there are two decisions left. How many of these control locations around the circumference do I pick? So, it's piecewise, constant curvature. So do I have like 10 points around the circumference or 20 or 5? That was the next question. And then how many of the total number of layers will I actually steer? Or do I just say this one is 0 degrees or it's a constant 90 and kind of make it easy on myself? And so this is where I'm going to leave you with a question to think about. What's a practical consideration when deciding on the number of design variables?